So we're going to finish up chapter 2. And before we do that, we have to review and go back a little bit into section 2.1. But then we'll finish that, move on to 2.2, and away we go. We're still working on our objectives and competencies. Okay. And I have some new study questions for section 2.2. So there they go. Here are some carryover chapter terms from 2.1, and here are some new chapter terms for 2.2. So make sure you have a good understanding of those terms and concepts. All right, and let's begin with community-based participatory research. Now, when it comes to trying to make community policy or government policy or something like that, it's important to get the community involved. So there are a lot of organizations and what we call community-based participatory research groups that do this very thing, where you have everybody getting together from just members of the community, healthcare professionals, researchers from universities, even business leaders, all getting together to help, again, to make health policy, okay, and to protect public health. That makes sense. I'm going to turn, I think my volume's up a little too loud. All right, so the core principles of this is simply those affected by research should participate in it. It shouldn't just be in a cold laboratory somewhere. Field workers, they need to get out and they need to work with the public and get them involved and get them educated. And that way they can help to protect themselves and reduce risk, which we will talk about. This is an equitable sharing of power. Again, it should not be removed from the community. This sort of research needs to incorporate the community if you really want to know how best to serve the community and provide good health care. Okay. Okay. And it does emphasize practical solutions. Like, what can we do? A good, before I move in, and again, usually there are specific community-based participatory research groups in specific communities. I saw a lot around Michigan. They really are big on this. So speaking of Michigan, let's just talk about Flint, for example. And believe it or not, there has been a CBPR group, or community-based participatory research group, that's been in place for decades and decades. And there was a lot of socioeconomic challenges facing people in this community, as well as all around Detroit, and that all had to do with the automotive industry moving out. So you have lots of people unemployed. You have an infrastructure that is crumbling. Hello, lead contamination. So there was a lot in place before we started to see the big problems with the lead contamination in the water. So Flint, for example, had Michigan State University College of Human Medicine, MSU, and Virginia Tech working in the community with the medical people in the community. Everybody working there together, monitoring the public's health, the population's health. Just a little bit about MSU. They have had a history of community engagement and public health advocacy for underserved families for quite some time. But it was especially a few physicians and some Virginia Tech researchers who were in the community that really started to publish some, some darning information against the water and the water quality. And of course, they found that there was in fact elevated blood levels found in children who were drinking Flint water. Okay, and here are some of the studies there. And so this particular report showed the increased incidence of lead in blood levels from 2.4 to 4.9% after the water source had changed in the Flint River. Now, we are going to talk more about this crisis when we get to specific water contaminants, intoxicants. But the study did a good job of comparing rates of people who lived inside of Flint versus those people who lived outside of Flint. And the people outside of Flint did not have any increase in lead levels in children. So this is what the study did. Now, even before that, but especially because of this, there was a lot of healthcare workers out into the community, educating people, trying to reduce all kinds of risk and exposures. But um, one of the things that was very helpful, because money is always helpful, the community and several areas around Detroit had some money from the Charles Stewart Mott Foundation. And because of that, they were able to provide medical education, public health research, and it was in place before, but it had grown, it expanded. And an advisory committee was formed, especially after the Flint water crisis. They were working with hospital partners as well as government agencies and even businesses, all there to reduce health disparities. And one of the things, of course, you probably saw the bottled water, just local businesses were trying to do their thing and just saying, this is what we can do now. So, this again is a way to involve everyone who has a stake in public health, and especially those who live in the community should be part of that, and that makes sense. This is the basis of community-based participatory research. So now we're going to delve into responding to environmental hazards to human health, and this is going to start with some math. But bear with me. Believe me, there's a lot of epidemiology that is involved in this particular chapter. I'm going to try to pare it down to the basics, so just bear with me, all right? Okay, so first of all, we're going to start talking about risk assessment, risk management, and risk communication. Risk assessment. Okay, so this is a regulatory science. People want data. I want to know, what is my risk? To find that out, there's going to be some math involved. And if you're going to make policy, you have to have some numbers there for regulators, okay? People in government, you have to have some numbers. So measuring risk, okay? Oops, measuring risks, so there. Okay, so why risk assessment? We do this because sometimes you have to be very clear about taking action, even though you don't have full scientific understanding of the hazard. You have to be able to say, okay, this is a risk, and this leads to disease or adverse health problems. So risk assessment sets default procedures for bridging gaps in scientific understanding. So, sometimes you have to just produce the math and say, okay, this exposure produces this, okay? So the basic framework for risk assessment: evaluate exposure and toxicity, bring this information together to characterize the health risk. Now, how do we do this? Well, just to rewind a little bit, really the best epidemiological study always provides comparison groups. This allows you to compare one group to another. This one was exposed, this one doesn't. So if you can do that, that is the best. Okay, so again, sort of rewinding and looking back at the first lecture, or excuse me, last week's lecture. Okay, we looked at certain kinds of studies. I reflected on those lectures, and well, one of the things you might have noticed about your textbook, they don't have a lot of pictures and figures, do they? Well, the same could also be said for the instructor materials. So sometimes I'm making my own flow charts here and going out into the web to find other images. So sometimes my flow charts look okay. This one looks okay. There's one that does not, but just bear with me. And so I wanted to use these flowcharts to really emphasize the difference between these certain kinds of study groups. And again, these are really great types of studies, if you can do them, that it will allow you to assess and measure risk, okay? So the gold standard, if at all possible, you would do a randomized experimental group. Okay, so this is experimental, it's analytical, right? You're going to have to, in this particular study, you're going to have to manipulate your population. So you're getting involved. It's not observational, it's experimental. You are manipulating and adding things and changing things. So if you could do a randomized experimental group study, then you would grab some random study people and say, you are a part of my population, and you can pick or choose. Okay, and probably you'd want to get people within the same, maybe age group, and you might want to have similar variables within that group. But then you'd say, okay, half of you, I'm going to expose you to a toxicant. Half of you, I am not going to do that. And then for those of you who were given an exposure, I'm just going to see, okay, did you get who in that group got disease, who didn't? How about in the non-exposed group? Okay, who got a disease and who did not? So this would clearly be able to let you know, all right, a certain exposure does or does not give you disease, and you can compare groups. This is the gold standard. However, you have a little problem with ethics here sometimes. It depends. You can't always use this. You can't just say, okay, we're going to get you together, people, and we're going to give you a toxicant. Yeah, that would be bad. You can't really do that at all. So you're limited to, well, I should say randomized studies are limited to non-punitive kinds of studies, you know, the kinds of things that you're not working with toxins, that sort of thing. We might give you some facial creams, you know, for wrinkles or something like that. So, you know, you can do this in lab animals. You can do this in animal bioassays. You can do that, but you can't do it in people. So just saying. Okay, so another group is the cohort study group. So cohorts, remember, this is the same group of people. They're kind of in a, you know, you have a similar population. The interesting and key part about a cohort study, sorry, is that you start with that population and you start with a healthy population, not even you know, with no disease apparent. And then you follow them over long periods of time, long periods of time. So cohort studies follow people over long periods of time. So we start off, say, with a population of nurses in your hospital, okay? And let's say they all graduated from nursing school. It's really great. Let's say this is the 1980s and they're fresh. They just started in nursing school, just got out of nursing school. And so we're going to study them over 20, 30 years. And okay. And what we're looking for, let's say someone had a hypothesis that nurses who are exposed to anti-cancer chemotherapeutics would themselves develop cancer because those drugs are carcinogenic. So, okay, they would start in the 80s and follow this population, this cohort of nurses over the decades. And then they would keep an eye on them and they would keep track of who was exposed, who wasn't exposed. And of the exposed people, who did not get a disease and who did. For those who had no exposure, was there anyone who still got disease, cancer, versus those who did not? This is when my graph went wonky. Sorry. So this is a great way to ask some questions and to test for a hypothesis. So you start off asking, you know, okay, is there, you know, will nurses who are exposed to anti-cancer drugs get cancer? So that's your hypothesis. This is great for hypothesis testing, but it takes a very long period of time. You start with healthy people. Okay. And again, you can ask the question, are exposed people more likely to develop disease over long periods of time? Okay, as opposed to case control studies, these work backwards from cohort actually, but you don't have that long time commitment. Okay, the way to know that it's a case control study, here's a hint. So on a test, if it has cases, people with disease, versus people without disease, and that's where you start, and they say control, okay, that's a case control study. Key terms, clues, okay? So again, this provides us a way to do some comparisons. People with disease are called the cases. People without disease are called the control. So if you look at the people with disease, the cases, okay, so they have disease. Were they exposed or not exposed? People without disease. Okay, so they're healthy, but were they still exposed or not exposed? So again, you can compare certain groups. So let's say people with the disease, okay, cases, they had really no exposure. Okay, so maybe you're linking one chemical to cancer. Yeah, that's not going to work. But if people with the disease were exposed in the past, and people without disease were not exposed in the past, okay, well, that's your case control study. So in this case, you would start with the nurses who already had or did not have disease. So now you can look at your hospital and go around, and that day just ask nurses, okay, of the nurses who have been diagnosed with cancer, how many of you have been exposed to anti-cancer chemotherapeutic agents? Okay. Hope that helps a little bit. Okay. So all of this requires calculation. If you're really going to figure this out, you're going to have a little bit of math, just a little tiny bit of algebra, not much. And this helps to link correlation to causation. What's the difference? So it's not too hard to have a correlation, but causation, really pinning it down to, okay, this is really the cause. Now that's the trick. Correlation does not always equal causation. Okay. This also, again, this goes down to, does exposure equal disease or adverse health outcome, period. So I have something kind of whimsical. This comes from Leon Gordis, 2013. It says carrots as a risk factor. So we can probably find there's a correlation between carrots and, adverse health effects. So, number one, nearly all sick people have eaten carrots, obviously. The effects are cumulative. Now, an estimated 99.9% of people who die from cancer and heart disease have eaten carrots. Okay, so there's a correlation, but is it a causation? Yeah, so that's a little different. Okay, so how do we know that a relationship between carrots and disease is causal? Okay, why is there a cause? Okay, does exposure to carrots equal disease or adverse health outcomes? Okay, so to figure this out, you got to calculate risk. It's going to be a ratio. That's plain and simple. Now, we do have to do some kind of calculation here. So I'm only going to do the easiest type of calculation you can do for risk, okay? But it is the most common measurement of risk, and this is called relative risk, also known as capital R, capital R. The most common measurement and one of the most easiest ways to calculate risk, okay? When you're done with this little calculation, so relative risk over here equals risk of disease in exposed persons over risk of non-exposed. Okay, so when we're all done, we'll have a number equal to 1. If there is a number equal to 1, that means there's no risk. If it's greater than 1, it's a risk. If it's less than 1, not only is it not a risk, it's actually protective. How can that be? Well, I have some images for you. So I've been busy. Google Images. Okay. So here we have some we have a population, and here we have some exposed, some unexposed. So these guys are exposed to some kind of factory, maybe possible toxicant. We don't know. So let's calculate relative risk, shall we, in this particular population? Okay, so looking down here, so I have those who are exposed, 1, 2, 3, 4, 5 over here, and then I have 7 unexposed here, okay? And of my exposed, I have, well, 4 of them are sick, but 1 is healthy. Over here, my unexposed, I have 6 who are healthy, but 1 who is sick. So can we do some kind of relative risk calculation? Yes, we can. What's the best way to do it? We can use something called a 2-by-2 contingency table. This allows us to record and analyze relationships. Do you remember way back when in biology class? Maybe you don't, but you would do do some genetic problems, do something called a Punnett square, maybe, and that allowed you to calculate probability, also a ratio. So, all right, so this is sort of like that. So here we have 2 rows. We have a row of exposed and a row of unexposed, and then we have columns of sick people, columns of well people, and then we do some totals here. Okay, so for our now to calculate relative risk, we just take, okay, so this cell would always be A. Sick and exposed is A. Exposed and well is always B. Sick and unexposed is C in this cell, and well and unexposed is always D. So set it up like this. To calculate relative risk, it's always just A divided by A plus B, divided over C plus D. Huh? Okay, so let's do the calculation. So A is 4. Okay, and then that would be divided by A plus B. 4 plus 1 is 5, 4 over 5. Okay, so, and then if we looked at down here in the denominator, we have C, which is 1, divided by C plus D, which is 1 plus 6 is 7. There we go here. So if we do this calculation, okay, this little algebraic equation, we get something like 0.8 over 0.14. And if you do that division, you have a relative risk of 5.6. Now, because that is greater than 1, we would say, aha, risk is high, looks like exposure is harmful. Okay. Let's do another one. Okay, so here's another group. Well, now there's more healthy people here that are being exposed. And in fact, well, it looks like half and half. Half exposed or sick and half are well, and half who are unexposed, well, are sick and half are well. So let's do that calculation. So if we have 3 sick and 3 well in the exposed, yeah, and 2 sick and 2 well in the unexposed here, well then, okay, now we have 3 over, okay, 3 plus 3 is 6, so 3 over 6, and we have 2 over, okay, 2 plus 2 is 4, so, okay, do that division in your head, 0.5 over 0.5, that's a relative risk of 1, so that's no risk. Okay, so being exposed to whatever is going on in that factory, not a problem. Okay, now how about this one? Factory's gone. I have like a vaccine up here. Okay, so how is this going to play out? So this group's been vaccinated, this group has not. Well, this is when you get a relative risk less than 1. Hopefully, hopefully that's what happens. So of those who are exposed, we have only 1 sick and 6 who are well. For those of you who were unexposed to the vaccine, well, we get more sick individuals. So 4 are sick and 1 is healthy or well. Again, do that calculation, and now you have 1 over 7. which is a 0.43-ish, and then you have 4/5, which is a 0.8. So you get a relative risk of a 0.54. So this means the exposure is protective. And this actually is true with vaccines. No vaccine is 100%. So even if you've had the vaccine, some people do not produce the antibodies. So their titer just doesn't go up and they don't seroconvert. So they are still at risk. So there you are. And there are some people who don't get a vaccine, but they still are going to be okay. So there you go. And that is true. That's just the way it works. Okay. More about that a little bit later on. So, what is risk? The risk is the likelihood of acquiring a health effect, disease or even death, something like that, or some adverse health effect, okay, of some kind. Risk assessment. This is all part of risk. We need to calculate risk when doing risk assessment. This examines potential health consequences from suspected exposures. So now we're looking at causal, okay? So we're trying to figure out, okay, this exposure, well, we're not at causal yet, but we're getting there, okay? So risk assessment comes down to a lot of things. What's the risk? And we can calculate that by relative risk. Can we quantify risk? Well, yes, by relative risk, we want to see, is it quantifiable and examines probability? Of course, we'd like that. So again, could cardiovascular disease be caused by particulate contamination in the air? So that is what we would want to do by risk assessment. And then finally, risk assessment, like I said, it's there to promote certain policies to protect public health. So there we are. Can we act on the risk to set up policies? And of course, this is all politics. Can't get away from politics, right? Okay. So looking at something, is it a hazard or a risk? Now, the two terms are not interchangeable. They are not. They make us alert, but no, they are different. Hazards, this means danger. It's qualitative. It means potential harm. It could mean toxicity for chemicals. Risk is the probability of harm, and it's quantitative. You know that math that we just did? Yeah, okay. Okay, so here's a good example, and I found this from the internet, which is quite nice. But again, okay, so sharks, they are a hazard. That's a hazard. But yet, is it, it's not a risk for this man because he's on the beach. So he's not really going to get any kind of exposure. So this individual, okay, so there's the hazard. And oh yeah, there's a risk because he's swimming with sharks. Same thing here. Now lightning, it is a hazard. But if you're protected, especially if you have a lightning rod, you're probably going to be okay. But the risk comes when you go out in the lightning, go out and you become exposed to the hazard, right? Okay, makes sense. Good. This is from your book. So this again, this is looking at the basic framework of a risk assessment. Identifying a hazard, again, it's something qualitative, looking at toxicity, that sort of thing. From there, okay, what's going on as far as, is it getting to the population? Is it entering the envelope, that sort of thing? So we look at dose response assessment, quantitative toxicity assessment, or sometimes if we don't have that, we can look at exposure assessment. And then from there, we can calculate risk and characterize risk. Okay? So this is going to harken back to our previous lecture, so bear with me. There are, again, fundamental assumptions about different chemical categories. And generally, we put them into two categories, those that cause cancer and those that don't. So when it comes to risk assessment that involves a carcinogenic chemical, okay, and the carcinogenic chemical effect, remember, there's no threshold. We don't have a minimum exposure, dose exposure that's okay. We don't have that. Instead, we calculate estimates of carcinogenic risk at very low doses, and that can be tricky. Usually we have to use animal models in order to do that. Okay, remember that. That'll come back. And then, of course, there are the non-carcinogenic chemical effects. And they have dose thresholds below which effects don't, we don't have any effects occurring. So we can calculate a lowest dose. And again, helps to make certain policies. Okay, therefore, key steps in risk assessment play out differently for cancer and non-cancer effects. You remember that from the last lecture, I hope? Okay, good. So, first of all, let's just go into detail with the non-carcinogenic effects. Your book goes into more detail than I will, but I'm going to hit on just the greatest hit, so here we go. Non-carcinogenic effects, again, are evaluated by comparing an exposure level or dose with the toxicity value, and where they overlap, that's where you get risk. All right, so when assessing a non-cancerous hazardous material and identifying them, well, okay, so you want to calculate exposure, right? So you do the exposure assessment. If you remember, okay, you're going to look at how much chemical toxicant, okay, is entering the envelope. Remember that. And it always depends on your individual's mass, their weight, especially fat content, that sort of thing. So it's milligrams of chemical per kilogram over the number of days they are exposed. And this is the way to do an exposure assessment, a way to measure or estimate dose, okay? Now, one of the things that, for policy making, you want to figure out, well, okay, so this is figuring out dose. Sometimes we're exposed to chemicals all the time. So is there a particular dose that will have no effect? So I can be exposed to this through many, many days, this amount through many, many days, and it won't hurt me. Let's say this is something in the environment and there's really no way to get rid of it or get rid of it effectively. So we need sort of a threshold here. We need, a reference dose. So a reference dose, look, capital R, little f, D. This is also calculated in milligrams of chemical per kilograms of individual times how many times you're dosed per day, okay? So we calculate that little threshold to figure out, okay, you can have this dose and it will have no adverse effects in sensitive people, even with lifelong exposure. So this is something that you do to set up policy. You kind of can draw a line on using a reference dose. So how are you going to do a reference dose and make that calculation? Well, I'm glad you asked. Oops, okay. We have our little mousy bioassays again. I know, don't think about it too much, okay? So, but they have to. They sacrificing themselves for science. Actually, you know what? In scientific labs, we don't say that we kill them, we say we sacrifice them. I know it's a word, but you'd be amazed. It's hard for people to work with these little guys because they are cute. I'm going too much on that. Okay, so when it comes to your RFD, okay, again, how can you get this from your rodents, from a dose response? Well, if you remember when we talked about the dose response curves before, and you had the no L, no effect, and the low L, okay, well, you can use those numbers. So you can using no L and low L, you can figure out an RFD. So even though that level, the RFD may not be toxic in mice, but does that translate to humans? Not always. So you have to take this into consideration. Before panels will give an RFD about a certain chemical, usually they have to get together and there's a lot of experts and opinions and calculations. And of course, the mice are going to be exposed a little bit more. They're going to have greater exposure. So you have to take that into consideration. But also, usually, whatever RFD, whatever the dose, usually you tend to take down the concentration a little bit more, just to make sure that you are protective and that you're not, sometimes it's hard to, to say that whatever happens in a mouse model is 100% relatable to a human model. So you want to err on the side of caution always. Now, what about carcinogenic effects? Is there going to be an RFD for this one? No, no thresholds. We're just going to assume if a chemical is carcinogenic, there is no safe level, period. So, how do we evaluate these chemicals, though? Surely there must be some sort of, some correlation between the amount of exposure and how large I am, how many days I am exposed. Isn't there something measured in that? And yes, we call that the cancer risk. So this is a probability of an individual in a population developing cancer over a lifetime, and we use those numbers, and we can use many, many studies to figure all of that out. So, for example, a good example of a cancer risk, the probability that we figure, that might come into play would be 0.00001 or 1 in 100,000 would be perhaps what we would say is your cancer risk if you are exposed to this particular toxicant, okay, or carcinogen. By the way, why 100,000? I'm going to pause for just a moment if you start to look at journals, you will see everything's in 100,000. Everyone reports in 100,000. Is there a real reason why they are always reported in like 1 in 100,000 or 0.01 in 100,000? There's no real reason. It's one of those things where people have always done it, so they just continue to do that whenever studying population effects and health exposure risks, things like that. They've always just used per 100,000. It just is. So, little side note there. Okay, so when it comes to the numbers, a way um, to categorize carcinogenicity, well, we tend just to put carcinogenic agents into certain groups. We put them into group one if we know that it is without a doubt carcinogenic to humans. There's 2A, there's a probability that it's carcinogenic to humans. There's a 2B is possibly carcinogenic to humans. Group 3, not classified as to carcinogenicity to humans. Group 4, probably not carcinogenic to humans. So if you're looking at a chemical and you're exposed to a chemical and you're looking it up in the IARC, you want to be in this range. You don't want to be here, and probably you'd rather not be there either. But group 4 is the better place to be. Okay, so risk assessment. Let's just go from, okay, so we're measuring risk. Now, how does that play into the whole scheme of things? Again, there is a 4-step risk assessment, all of which we've been talking about all along. So number 1, hazard identification with what health problems are caused by the pollutant. So again, you can do, there's all of the things that we've already talked about as far as risk assessment. Calculations as far as risk. From there, we go to exposure assessment. How much of the pollutant do people inhale or ingest during a specific period of time? How many people are exposed? And again, it's ingested or came into contact with. We also look at dose response assessment. What are the health problems at different exposures? So, okay, again, dose, dose makes the poison. So how much of a dose did you get? And then finally, all of this comes down to risk characterization, and that's the last of the 4 steps. So what is the extra risk of health problems in the exposed population? Again, brought down to some kind of probability. And this table, and I'm not going to go into this in great detail, but this just shows using the 4 major steps in risk assessment as it applies to toxicology, so a chemical. Here you have non-cancer effects. Here we have cancer effects as it applies to exposure assessment, hazard identification, dose response assessment, and risk characterization, all of the things that we've talked about. So there you go. It just kind of pulls it all in. Okay. Little bit of the challenges that are associated with risk assessment. Sometimes these numbers are hard to come by. You have people out there, uh, uh, community healthcare workers, you have epidemiologists and scientists out there, but you know, sometimes it's really hard if you're going to do a study. And again, it's really well, if you remember statistics, the bigger the number, the sample size, the better. And of course, you want to have groups to compare with. And it's hard to get real tangible numbers if your group and sample size is really small. So sometimes it's really hard to get large sample sizes. Risk estimates can be really, really low if your group is low sometimes. So yeah, you need sometimes you need to have large exposures. Flint with the lead in the water, unfortunately, there was a large sample size, so that was a good research size, unfortunately, for the people of Flint. There are a lot of environmental factors that come into play. Sometimes it just takes a very long time to cause disease. Some things, again, we talked about mutations and causing cancers, and many times there's a lot of steps that are involved. Well, how do we find out that you have been exposed to this one chemical during in let's say 2012? Do you remember where you were in 2012? Not so much. And it could take a very long period of time before the effects of the exposure come about. So it's a challenge. And again, there could be multiple causes of the disease, not just one chemical. But there you have that synergism. Two factors together have a stronger impact than they would if they acted independently. And sometimes the answers aren't black and white. You start to get, some numbers, and you can say, okay, there seems to be a correlation, but we're not positive about causation. We're not sure about everything. Okay. Okay. So risk assessment as a regulatory science, you get all of this data. And then, okay, where do you go from there? Okay, well then hopefully uh, we can talk to people in the community, government agencies, and say, okay, we need to regulate certain substances and certain exposures, and okay, then hopefully we can go into risk management. So from assessment to action. All right. So, risk management, in this case, actions are taken, like I said, often by government agencies to control or reduce environmental risks to health. We would hope. Okay. This considers the magnitude of the health risk, regulatory framework. Okay, what can you do? What can't you do? Technical options for controlling the hazard. I mean, is it loose in the ocean and it's gone, gone, gone? What is the cost of controlling or reducing the environmental risk? And we, of course, always have to look at the social context. And that would include environmental justice that says, okay, everybody, no matter who you are, okay, you should have clean water, you should have clean air. So, okay, all of that is important, and this is all part of risk management. Okay. So, when it comes to risk management for individual chemicals and sites, so you have areas like around Flint, Michigan, or you have an old factory or something like that. Okay, so what do you look at? Well, again, chemicals in drinking water, in the air, in the workspace. So you have to make decisions about goals for standards. Okay, so how much you have to measure, what is in the water, what is, sometimes you have to look for a reference dose and say, well, you can be exposed to this much. Most people can be exposed to this much over long periods of time, and it's okay. Sometimes you have to make decisions about certain standards. Okay, is this something that we can do? If we shut down one drinking supply, okay, is there going to be another drinking supply? And that was one of the problems that did enter into Flint, actually. So, okay, that's a problem. But again, if you do have a contaminated site, there's a lot of things that you have to worry about. The problems are complex. A lot of times you could have multiple chemicals. Now, I'm not really talking about Flint, but we could talk about, sometimes you will build, well, around Omaha, actually, around the riverfront, there was a toxic chemical plant that was there at one site, and they're rather limited as far as what they can do to that property there, because there's probably lots of chemicals, and you've got it's right next to the river. It could leach into the river. You don't want to release that. It can maybe be released as dust. It's in the soil. So there's a lot of complex problems here. You have to look at toxicity, future uses of the site, effectiveness of cleanup options, and costs. Um, okay, again, again, looking at okay, what's an acceptable risk? The acceptable risk is the lowest risk that can be reasonably achieved technically and financially. So the riverfront area is okay, that's in the center of sort of where a lot of things occur in downtown Omaha. We have the College World Series. Can you just leave? I mean, what can you do with that property? Um, and again, people have to go in, they have to measure, and they have to find, okay, what is an acceptable risk? And there has to be a lot of probability, a lot of that math going into it. But another very good. So, what is the level of risk acceptable? Here's another example of this that I really like. Let's go back to DDT. If you remember, DDT was a pesticide, and it was used widely until Rachel Carson's Silent Spring said that, okay, this DDT is killing our birds, our predatory birds, and it probably has an impact on humans as well. But the thing is that, well, during that, when DDT was being manufactured, it was being manufactured a lot. So we know how to manufacture it in huge quantities, so it's cheap. There are certain communities that are at risk of contracting vector-borne diseases. What do I mean by that? Well, if you live in an area where mosquitoes carry the malaria parasite, and it's in your home, it's everywhere you go, and how are you going to sleep without being a mosquito meal and getting malaria injected into your bloodstream? So, and when food, I mean, you're lucky to get food. So, how are you going to control insects? Well, we have this chemical. It's really, really cheap. Government agencies in these areas, especially Africa, they're like, okay, well, we can't afford to buy fancy pesticides and do other, risk management procedures. So, we're just going to keep using DDT because it's cheap. Well, what do you do? So, and it still is used. Unfortunately, again, it's not very effective in some areas because the mosquitoes have developed resistance against it, just like bacteria develop resistance against their poison, known as antibiotics. Now, so we have to, but people in those communities think, and the the government regulatory bodies think that there is an acceptable risk here. Okay, well, if I don't have DDT, then the mosquitoes bite me and my family, we get malaria and die, which is a possibility. So maybe we have to consider that an acceptable risk, unfortunately. There's also something called a negligible risk. Truly, if you're going to do a risk assessment and you come back with, okay, there's really not a risk here, and we don't need to be concerned. Well, this is great for a risk manager, so then we don't have to worry about it. So a negligible risk means the risk is too low to be concerned. So there you go. Okay. Other examples of risk management. Maybe put limits on emissions, or if there's waste, there are requirements to treat waste. So, for example, back in the day, when I was driving, way back when, I drove an AMC Pacer. Yeah, feel sorry for me. If you don't know what that car is, you should Google it for a good laugh. Anyway, back in the day, you could choose your gasoline type. You could choose leaded or unleaded. Now, leaded typically had a higher octane, but lead in the air, okay, not good. So now gasoline sold to, well, for our cars or vehicles, leaded gasoline is no longer available. But when it comes to the aviation industry, okay, well, smaller planes, most of those planes still use leaded gasoline for high octane. Now, this does not include jets. So if you live by an airport and you see the jets going over, well, you don't have to worry at least about lead, but the small planes, and they are considerable producer of lead emissions. So the lead's in the air, it gets into the soil, and there you are. So we can limit emissions. That's one thing. We kind of need to move a little bit on those small engine planes. We can change industrial processes. So, for example, if there is a hazardous process, we can do something that is less hazardous in the workplace. That makes sense. For industry and for people, we can give you an incentive for complying to guidelines of risk management of certain chemicals and pollutants. So, okay, maybe we'll give you a tax break. Yeah, okay, you didn't release too much CO2 in the atmosphere. Yay for you. Tax break. Oh, no, you released too much CO2 in the atmosphere. We're going to give you a tax penalty. You did not comply. Shame, shame. Publicly available information as an incentive. And there's a lot that you could do that way. But one of the things that works is that, well, you can make the public available or the information available to the public that, okay, this company is very compliant. This company is not compliant. And well, here are some of the things you're exposed to and the possible risks. Okay. And of course, the work of local health departments, and they're always busy with risk management. How about risk communication? Okay, this can be tricky, and it has to be a two-way street. You have to have someone not just talking, but someone listening. So, and that's tough sometimes. There are challenges. So, when it comes to risk communication about environmental health hazards, well, there should be a good exchange of information about a hazard between experts and those affected. But sometimes the public perspective of environmental health risks um, is not what the risk management community think of as far as a risk. So let's just say the two sides don't share the same perspective of risk. You know, you have the public health officials saying, here's the probability, but you have the public who have heard an awful lot of negative information. They are outraged. So you have something called the outrage factor. So this is just, what happens when the public opposes a policy and it's not based on knowledge or any technical details. So there's a lot of very good examples of this, but basically it has to do with emotion. People get worked up, and yes, we could say the media has a lot to do with that. We know we're always dying of something. If it's not SARS, it's Ebola and it's Zika. And not that those things are not important, they are, but for crying out loud, settle down. So again, you have people in industry, people in the sciences saying, well, this is your probability, but people aren't hearing that. They're thinking risk, hazard. How could you expose us to this? So it becomes very, very difficult for people in this particular position and in these fields. So, again, specific features of environmental hazards do generate outrage. Now, this is not to say sometimes it isn't well-founded, but when it comes to the hazard plus outrage effect, this means that it's uh, no information is being acceptable. So it's a difference in perspectives, and you can't have two sides really agreeing. And that's bad. That's going to certainly stop communication, isn't it? So that everything that a public healthcare official says is going to just probably add to the outrage of the public. So very, very difficult. Here's my favorite example. Measles, mumps, and rubella, the vaccines cause autism, right? Well, that was big. Unfortunately, it still is. So there was a lot of press at the turn of the century. In 2001, it became so emotional. The outrage was so um, what should I say, so prevalent. It was even changing government, well, it was even changing policy throughout the whole world. And the scientific community came out, and there was a April 23rd, 2001 Institute of Medical report that says, okay, there's no evidence, okay, of a causal relationship between the measles, mumps, and rubella vaccine and the autistic spectrum disorder individuals. Between those populations, we can't find any causal relationship here. The panel, the committee that this reported on, that was reporting this, could not even find a proven biological mechanism that would explain such a relationship. Okay. Now this is from CNN in 2008, but this didn't stop people from believing that giving children vaccines was going to cause autistic spectrum disorders, okay? Because there are more and more cases being diagnosed of as far as cases of autism, right? The cases are increasing over time. People want to know why. They want to know why now. And somebody said, yeah, vaccines. Okay. There was even a young girl, 9-year-old Hannah Poling. Now, she had autism, and she was awarded a very large monetary compensation, she and her family, which I can't really say was really bad. I'm glad for her and her family. But here is the thing. You have to know that, and the reason they gave her the money, they could not find a causal relationship. They could not. But in the courtroom, people in the courtroom, they also have emotions. And everybody was caught up in the anti-vaccine frenzy. So the argument was that her illness, and she had other problems, but that it had been significantly aggravated by vaccines that she received as a toddler. So, but understand, she was born with a mitochondrial problem. Do you remember your cell biology basic? This is a nucleus, this is the mitochondrion. If a cell is like a city, and in my world, a cell is like a city, the mitochondrion is the power plant. So if your power plant in your city doesn't operate well, and all of your cities aren't operating well, there are going to be multiple problems. Now, is it possible that the vaccine, and actually it's a component of the vaccine called thimerosal, aggravated the problem? I don't know. And neither did the scientists. No one's been able to figure that out. But she got the money. Do you understand where you have to get when it comes to risk assessment, you need the numbers. You need to find a causal effect. But sometimes emotion gets in the way. So measles vaccines cause autism. Okay, or measles vaccines cause autism. I need to change that. Lots of press, and again, sorry, that was a repeat. And that's what led to everyone believing Andrew Wakefield, right? And I brought this back not just to show you, of course, here you have the outrage factor. Pharmaceutical companies are lying and killing babies. And that's, if you go online, there are images that are horrific that show, there's one, and I was going to post this, but I just can't stand the image. There's a picture of a baby with like needles sticking all over it. And I thought, okay, really, people, yeah, here's something. People in the pharmaceutical industry, it is true, they do have to worry about the bottom line. And yes, it's true, they have to make a profit. And yes, there sometimes are problems. But remember that they live in the community and they have babies. They have, nieces and nephews and grandchildren and things like that. In any population of people, you're always going to find someone who is unethical and darn right immoral. So whether it comes from the scientific community, the medical community, or just somebody who's doing your plumbing, okay, you can't escape that, but you have to just be careful. And just once again, this was actually published in the Lancet of all things. And this just shows how outrage can occur in people who are even educated, who ignore just they can even look at the data and see that this is nonsense. But this is what outrage will do and how it will change public opinion. But unfortunately, we're left with this terrible taste in our mouth that giving our children a protective vaccine might ultimately give them a very serious disease or even kill them, right? So even though you have the facts, now the fear is there. Years ago, one of my professors said, he said, I can make you afraid within minutes and it will stick. He said, education takes years, and it is almost always an uphill battle once I have made you afraid. And that is true. But this is what, if you just go to buy a used car, one of the things they're going to tell you is, a couple was looking at that car earlier. I think they're going to come back. So you better snatch this up now. So this is the way we sell people. We make them afraid, and sometimes it manipulates public opinion in a way that it should not. So be careful. That's all I'm saying. Okay. How about some real numbers here? Instead of 12 random children, Denmark did a study between, 1991 and 1998. Here's a 7-year study. It looked at over 440,000 vaccinated children and almost 97 unvaccinated children. Hey, we have groups to compare. Isn't that nice? So then it was followed over a long period of time. And did one group have a higher rate of autism than the other? No, they did not. Okay, Japan, because they were so caught up in the outrage factor that they even suspended measles, mumps, and rubella vaccines in 2005. Well, you would think the autism rate would decrease, right? Nope. Autism rates continue to decline. Here's a wonderful study from Finland. 14 years of studying 1.8 million children. And okay, so looking at children that have had the measles, mumps, and rubella, and trying to find a link, and they can't find any link between the vaccine and autism, looking at vaccinated versus unvaccinated children. So, okay, what do we know about autism? It is an it is in an incline. This is true. We're not sure of all the reasons, but remember I said, okay, genetics loads the gun, the environment pulls the trigger. Most things usually have several events that take place. This is probably true with autism. We know that there's a lot of things going on in autistic people. It's on a cellular level. So, of course, we know it's going to have a genetic component. Usually, this is identified in toddlers from 18 to 30 months of age. But again, we still don't know the cause or causes, but we do know that there's probably a genetic link. Little side note, before a child has even been vaccinated, in the wound, you can predict whether a child will have some autistic spectrum disorders based on how the placenta is folding. So there, so that's one of the things that we know as well. That's a little side note. But okay, here's some other things that makes it difficult when people say, okay, we can't find a causal relationship between vaccines and autism. Okay, but sometimes you're looking at animal studies and you hear something, well, they found this in animals, but then it doesn't translate into human studies. And this is true all the time. And sometimes this sort of makes people not trust the science and the scientific community. Well, here's an example, moving away from autism. You know how they're always finding a cure for cancer in an animal, but it doesn't translate to humans. So why don't we have that in humans? Because again, animals are different than humans, and you have to. Sometimes you can make comparisons, but sometimes you cannot. There are other factors involved. Also, people get very upset because sometimes scientists don't commit to an opinion. And you know what? That's actually not a bad thing, because here's the thing. Here's the thing about science and scientists. They're there to seek the truth. It's not, rarely do you get black and white, yes and no answers from science. You start with little tiny experiments that give you little tiny pieces of the puzzle. And sometimes you come up with what you think are all the pieces of the puzzle, and then another scientist with another experiment says, no, we have to change this a little bit. What you said is not quite accurate. It's a process. This is the only way science works. All of our science today is based on science that occurred, throughout, decades and sometimes centuries. You know how people are always laughing about, oh yeah, well, there's this study to study, proteins and fluorescing jellyfish. Why do we care about that? Well, scientists who found a fluorescing protein in jellyfish won Nobel Prizes because that is used in so many cell biology experiments now, and we can track development, embryonic development, and figure out what genes are affecting normal development of a fetus and abnormal development in a fetus. Everything builds. So generally, when you have a scientist, when a true scientist who isn't trying to sell you something, they won't say, oh, this causes that. They will probably say something along the line of, well, there's a lot of evidence that supports that there is a causal relationship between this and that. Okay? They will say this is where we find the evidence. Sometimes they'll say the evidence is overwhelming. But until you get to a scientific theory, that's what you have. We say overwhelming evidence. So who can you believe? Who can you trust? Well, sometimes we forget. We're so bombarded by stuff on the YouTube, on the television, on YouTube, on the radio. People have opinions, and they sometimes say them very loudly. So, number one, the person who is speaking, what's their educational background and training? Do they have a conflict of interest? That's a big one. Look for that one. When it came to climate change, a lot of the experts against climate change, yeah, they had a real vested interest in disagreeing with a lot of the evidence. Has the expert done research or taught in the field? Have they published reputable journals and sources? Can that person even admit that there might be a problem with their results and information, or or information is lacking, or maybe someone who disagrees with them might have a point? Ah, well, those people are hard to find, but try to find that. Okay. And by the way, I love this. So here's Jenny McCarthy. I will guarantee you that she looks better in a Playboy bunny suit than I ever have. Okay, probably even at her age. But she is not a vaccine expert. I'm guessing I'd probably have had a little more epidemiology and immunology and cell biology than she has. But she's people consider her an expert. So, and a lot of people hear this and they believe it. Now, she is emotional about the fact that her son was born with autism. She wants an answer. And she is outraged at the thought that the vaccine that she allowed to be given to her son might have caused that autism. But I think she has to look elsewhere. Okay. So in communicating risk, how do you do this? Well, okay, number one. So in the community, when you're educating people, use simple language. Do not make assumptions about your population. Sometimes they have a wide range of literacy. Don't hand them a pamphlet. I worked for Hope Medical Outreach Coalition, and I made a big blunder when I had a gentleman at Francis House read some literature, and yeah, I was young, and I had no idea that the poor man might not have been literate. So to this day, I just cringe, but I just was ignorant about the fact. So now I know better. Um, Understand social and cultural contexts, when communicating with them. Try to determine the characteristics of your target audience. So use several resources, and that might help. So you can use TV, radio, podcasts are really big right now. Printed information, newspapers, and really nice, colorful brochures. So again, about Zika and sex, there you go, something very colorful. This is from the CDC. So you have to do this in many different ways and communicate as best you can. Okay, so precautionary approaches in environmental health policy. So couple things to talk about here. Okay, so the precautionary principle or the precautionary approach. And so, well, in the previously, we've talked about, okay, what to do to manage risk and exposure, and basically it's sort of after the fact, but maybe we wanted to be a little proactive. So before the problem hits, maybe we can identify that this might be a hazard and stop it from happening to protect the public. So early warnings of serious harm from a substance or activity call for precautionary measures to be taken before there is even clear proof of harm. So, and that's great. But, the person then that gives the early warnings of harm, well, they're the ones that kind of have to, they have to have the burden of proof. So prove it. So if we're going to go through all these precautionary measures, where is your proof? Okay, so that can be a little difficult. So examples of precautionary approaches that have been taken. So internationally, of course, we have the Kyoto Protocol on global climate change. So we've got the red flags, and we're trying to get together to stop all of the global climate change factors. Okay, all the things that are causing climate change. We're trying to stop them before it gets too far out of hand. There's also the Montreal Protocol on ozone depleting chemicals, because we like ozone, right? So those are some examples of precautionary principles or approaches. Now, in addition to that, now this one's very interesting. There is something called the U.S. Toxic Substances Control Act. So, okay, so we can stop chemicals from being released, even though there might be some evidence that it might be hazardous. Okay, that might be a risk. Okay, well, who is going to be responsible for showing the risk? Unfortunately, the Environmental Protection Agency is responsible, not the companies who manufacture the products, but the EPA. So, okay. So the U.S. Toxic Substance Control Act now requires the Environmental Protection Agency to determine whether a chemical is likely to meet a safety standard. So some kind of untested standard. Okay. Before it even enters the market. Okay. Um, there's one other thing, and I'm going to come back to the EPA and the U.S. Toxic Substance Control Act, TSCA. This is the European Union's REACH program for new chemicals. This is something that they have out in just the whole European Union, and they say that chemicals have to have toxicity tested before authorization. So on the right-hand side, this is these are tags that appeared on a garment. Now I am a plus size lady, so I'm also tall. So I tend to shop in many different places, and because I've traveled, I know that there is a company by the name of Ula Popkin. And now they are based out of the United States, but they sell a lot in Germany and in the Netherlands. So here they have, because they do sell overseas in the European Union, I just love this. And this is a little different, I know, than exactly the REACH program. But this is confidence in textiles. Tested for harmful substances according to and I'm not even quite sure what the standard is, but here it is in German if you wanted to see that. So I thought, yay, could we please do that? Back to the EPA. So the EPA is in charge of seeing to all of these chemicals and all the new chemicals that are being released in the market, and we're not even sure how many they are. Just so you know, they're overworked and under-resourced as it is. And this little graph just shows it's been a little difficult to fund the EPA. Little dip here, I wasn't aware, but it kind of went up and it went down, and here it went all the way up, and now it's dipping. And with the new administration, there's probably going to be uh, another dip in EPA funding, which is, I think, dangerous because we're releasing more and more chemicals. And if the EPA is the one that is going to determine, okay, that we have these possible health threats, then okay, shouldn't we have them funded a little better? Just saying. Okay, so as far as the precautionary approach, and wouldn't it be nice to stop the release of chemicals until after they have been proved safe? Just to, that would be such a nice thing, but we have lost some opportunities already for this particular approach. Because of the long-term use of asbestos, we're still trying to deal with that. People are still exposed to asbestos. I have a cousin whose house still has asbestos in his shingles. I know, right? All kinds of synthetic organic chemicals that we know are linked to a lot of problems. Let's just say the evidence highly suggests that there is a significant health risk when exposed to these synthetic organic chemicals. The lack of global fisheries, which we really haven't talked about, and the food industry. And this book really loves mad cow disease. Well, so do I. But yes, a little story about mad cow disease. Well, again, the food industry used to feed back bits and pieces of cows back into the cow population, which again spread mad cow disease. But and we did stop that transmission of prion mad cow disease here. Great Britain did not, unfortunately, and yes, they got into trouble, clearly. So, okay, let's talk about something called the Consensus Conference. That is kind of nice. It's an interesting way to, again, be a little proactive and help policy making. So there's something called the Danish Style Consensus Conference, and this is a conference that is usually held on very complex issues. Usually it's over a 3-day period, although sometimes it runs a little longer. But again, it is relevant to current policy making. And even though it's called Danish Style Consensus Conferences, um, Denmark, of course, is they spearheaded this, and they've been doing this for decades now, but other countries have adopted this as well. So as I said, it's a 3-day process, and you have a group of citizens, okay? And they are briefed, and then, they are able to ask a panel of quote unquote experts, scientists, engineers, medical people, all experts in their field. So regular citizens are being involved, and I like this. And they, based on the information that they gather, they release a report, and this has a direct relation on government policy and protecting the public. And again, and it may be sometimes it's for proactive risks, sometimes it's a little retroactive, but there you go. But again, it's all about public participation in the development of scientific knowledge and public health. Okay, and then finally, wrapping things up, there's the health impact assessment. That's a little bit like the consensus, well, it's a little bit kind of a mixture between the precautionary principle and the consensus conference, just a little bit. And so, okay, what this is, it's an assessment of likely population health impacts of a proposed policy or action before it is implemented. So again, looking at it, being proactive. And what they look at is impacts on vulnerable subgroups. It includes positive and negative impacts and seeks input from affected communities before decisions are made. So yay, little bit of a combination of both. Okay, so this was a very long lecture, and I'm glad you stayed with me there. There's only one more thing that is associated with this particular lecture, and that's the review. So make sure you look and listen to the review and participate. Okay, have a good one.